So, okay, welcome back. And we continue with the second lecture of today. And this is given by Eve Ostriker. Yesterday, she gave a beautiful lecture on the interstellar medium. Now she goes on, and I understand she will telling us how molecular clouds form their stars.
Great, thank you very much. So today is the second of my three lectures. And yesterday we talked about um, the large scales. What is the interstellar medium? Kind of what are the different phases? What are the processes that are physical processes that are important in the ISM at a microscopic scale? And today I will be moving on to molecular clouds and how individual molecular clouds form stars, and also starting off with talking about the empirical results on the association between star formation and molecular gas. So this montage I think, gives you a sense of the tremendous range of scale that is involved in star formation. So imagine that you're starting out with diffuse gas, which has average density, say, of about 1, and you're ending up at the density of about 10 to the 24 particles per cubic centimeter. So that's many orders of magnitude in density, 24 orders of magnitude in density, and it's correspondingly 10 to the 8 in size scale. So it's a huge dynamic range in these processes, in the process that leads from the diffuse interstellar gas to individual stars. And this is, it's a tough call if you're thinking about simulating it. So that's why people don't, go from the scale of the diffuse interstellar medium, resolving galaxies all the way down to individual stars. Generally, we break this up into different stages. So simulating the diffuse ISM, then simulating molecular clouds, and simulating core collapse and accretion within stars. Maybe we can hope that over time, when you're all giving these lectures, there will be a possibility of going from extending the dynamic range within any individual simulation. But for the time being, we do tend to break this up into different scales. And it's also observationally broken up into different scales when in characterizing the relationship between star formation and gas. And I'll just say a few words here. So this is, you recognize this part, but going down to these scales. So these are these are starless cores found from Herschel this is a half a parsec scale. So these dense cores are a tenth of a parsec, and I'll talk more about them. And then this is, of course, HL tau. There's a chalk version of that out on one of the blackboards. So you can decide whether it looks like that amoeba outside in the lunchroom. Okay, so just an overview first of when we think about star formation, we're really thinking about star formation within the life cycle of the interstellar medium, because it's not a one-way process. Star formation is part of a cycle. There are many, our galaxy is billions of years old. The time scale to go from essentially, the largest scales down to individual stars is really only 10 to the 7 or 8 years. So our galaxy is very old compared to that. So what's the progression in this cycle, going around this cycle? Well, you're starting with diffuse gas. Out of this diffuse gas, which has an average density of, say, about 1, a large piece of that is collected from a few hundred parsecs to make a giant molecular cloud at higher density. So the average density within a GMC might be about 100 particles per cubic centimeter. Quite low temperature, as I discussed yesterday, in molecular gas. So within this GMC, there are turbulent motions, which are highly supersonic, hypersonic indeed, and they can drive shocks that compress the gas to much higher densities. So the post-shock density for an isothermal shock goes as the square of the Mach number. Of course, these clouds are magnetized, so that means that in the direction perpendicular to the magnetic field, the enhancement goes as the Alfvén Mach number, but there are motions in all directions, so that means that you can get enhancements up to a factor of 100 in an individual shock. So within these densest regions in clouds, there's post-shock dense regions. The structure tends to be filamentary rather than huge sheets, basically because the turbulence breaks this up. And within these filamentary regions, the densest parts of them then can contract to make individual prestellar cores. So the typical numbers for these are density masses of 1/10 of a solar mass up to maybe about 10 solar masses, and densities, which are now much higher, 10,000 to 1,000,000 particles per cubic centimeter. So it's these structures that can collapse to make an individual star disk system. Of course, these disks can then evolve to make planets, which is good for us. So among those stars, some of them will be very massive, and those massive stars are quite luminous. We know that there's a relationship between luminosity and mass. And in particular, they emit UV radiation, which can ionize their environment, and that ionization raises the temperature from 10 degrees to 10,000 degrees. So there's an immediate, very large enhancement in the pressure. That overpressure tends to cause a rapid expansion, and we'll talk about that in my third lecture on Thursday. The more massive among these massive stars can end their lives as supernovae, and that has an even more dramatic effects on the environment in the blast wave that expands, that is produced by this sudden injection of energy. So these feedback processes are important in dispersing the material that collected to make a GMC, but it's also important on larger scales in the ISM. This is really the main source of energy, and I'll talk about that in my lecture on Thursday. But this is a cycle, and in this cycle, there will be so gas gets dispersed, but someplace else in the ISM, gas is now able to form gravitationally because the turbulence has dissipated enough, because there's high enough densities, and so some other location, a new GMC is able to form and start the cycle again. So what I'll be talking about today is the first of these two topics, the dynamics within molecular clouds and star formation. And then on Thursday, I'll be talking about the self-regulation part of the cycle. Okay, so here are the sort of subtopics of my lecture today, and I'll start with what are the empirical relationships between the molecular gas on large scales and on cloud scales with star formation. So I showed you this set of pictures yesterday. And this shows some of the kiloparsec scale surveys of molecular and atomic gas and signatures of star formation. So this, in the bottom here, this shows some GALAX maps as well as Spitzer maps. So these are all kind of kiloparsec scale. And star formation rates are either the rate of star formation is generally inferred in a number of different ways. One is by so you can use H alpha, you can use UV, you can use infrared. These are all can be turned into signatures of star formation by calibration. They are sensitive to different durations in the sense that the UV is not UV can be emitted by stars that have a range of ages up to about 10 to the 8th year. So that's really more an average of star formation over the last 10 to the 8th years, rather as opposed to if you're looking at H alpha, that's really looking at stars that are less than about 5 million years old. So for different spectral signatures, we'll tell you about star formation that's either averaged over a longer time or a shorter time. And as I mentioned yesterday, we're now moving to much larger surveys, so over a wider range of galaxies, and also much higher resolution. So this is the FANGs. This is PAWS, actually, pre-FANGs, at 40 parsec resolution in M51, and you can see there's very high resolution now of the gas, and this is moving to a much larger sample of galaxies. So as I'll talk about, that enables the resolution of individual GMCs. Okay, so what do we see from the relationship between star formation signatures, either in UV, 24 micron, H alpha, all appropriately put together to correct for the fact that, for example, H alpha has to be corrected for extinction in molecular environments, and you do that in part by using the infrared, because the radiation that the UV radiation that was absorbed by dust is then re-emitted in the infrared. So I won't go into the details of that, but this is just, so if you see that FUV plus 24 micron, that's basically putting together the UV plus the infrared to get a measure of the star formation rate. And on the horizontal axis here, this is the inferred H2 surface density, which is inferred from CO. And I talked about yesterday, there are, in fact, issues about how you'd convert CO into H2. This just adopts a constant value of the conversion factor. So what is shown here is from a number of different galaxies, the relationship between star formation rate and molecular gas at kiloparsec scales. So this is basically taking a beam of about kiloparsec scale. These are individual beams in many galaxies. And you can see that there's an approximately linear relationship between the star formation rate and the molecular gas mass or surface density. So that is then, so observationally, this is often described in terms of a depletion time. So the depletion time is just obtained by taking the star formation rate and dividing by the gas, or going the other way, taking the gas and dividing by the star formation rate. That gives the depletion time. And the typical value of the depletion time is about 1 billion years in nearby galaxies. And that's true both for large spiral galaxies and also dwarf galaxies. So what's shown on the left here is for the Magellanic Clouds. So the blue is all of these, this is from the Heracles survey. These individual points are from the LMC and SMC. And you can see that these depletion times are fairly similar. There may be a factor of few shorter, but even for low metallicity dwarf galaxies, there's not a big difference in the depletion time. So that says that star formation is not very sensitive to that either the galactic environment, that is, whether it's a large galaxy or a dwarf galaxy, and it's also not that sensitive to the metallicity. Okay, and this shows that even going to so each of these pink points here is the gas surface density of molecules, but this is even in regions that are not molecule dominated. So even in regions that are not molecule dominated, the star formation rate scales roughly linearly with the amount of molecular gas. And this is now, so that was all at kiloparsec scales. You can do the same thing now at higher resolution at about, this is for M51 now down to 40 parsec scales. And you can see that this depletion time is still about a couple of gigayears. But one thing that you can see right away is that there's more scatter. So at higher resolution, there's more scatter. So this is from 10 arc second, that's from 30 arc second. So there's more scatter when you go to higher resolution. That's because as you go to higher resolution, you may be catching within your beam, the molecular material may have dispersed and you're only preferentially looking at stars, or it may be an early stage in the cloud where the stars have not yet formed. So generally going to higher resolution, there's more scatter in the relationship between star formation and gas. Okay. So that's the kind of lowest order. At lowest order, roughly star formation rates are proportional to the molecular gas mass. But if you look in more detail, it's more subtle. And so this is showing now as a function of radius in a number of galaxies. This is from the EDGE survey over here on the right. And this is from, I think this is just M51, but let me see. Yes. But the main point here is that the depletion time is lower in the centers of galaxies. So that's saying that if you're looking just in some given at some characteristic density, as you would get from the characteristic density of needed to excite the 1 to 0 or 2 to 1 transition of CO, then the depletion time is actually shorter under some conditions, as would prevail in the centers of galaxies. So that's in the centers of normal galaxies, but you can look in the centers of starburst galaxies, so where the densities are actually much higher, and there's you see quite a different relationship. So what's shown here on the left is star formation rate as a function just of the total molecular emission. Here is applying two different XCO factors for the centers of galaxies and for the larger scale. So if you apply two different conversion factors, you get out of what looked like a unimodal distribution, you get basically a kind of bimodal distribution. Maybe that shouldn't be too surprising. But this was, there had been an idea that there's a given smaller XCO factor for starbursts than there is for normal galaxies. But really, there's no reason there should be, the CO does not know about what kind of galaxy it's in. It only knows about the molecular conditions. So although we think that there should be a variation in XCO as a function of conditions, there's no particular reason it should be a bimodal relationship that's different just in the centers of galaxies versus large scales. And so this is using this continuous continuous function as the conversion factor from CO to molecular gas, as I talked about this yesterday, that you can get from radiative transfer models applied to simulations. And using that conversion factor, instead of a linear relationship at very high surface densities, there's a quadratic relationship between star formation rate and molecular gas content. So that's showing that you wouldn't see that if you were just looking down here. This is the range of surface density of kind of normal galaxies, but when in starburst regions, the surface density gets much higher, and there you start to see this, as opposed to slightly shorter depletion times in the centers of normal galaxies, you get much shorter depletion times in the centers of starburst galaxies. So it becomes strongly nonlinear in that regime. Okay, so that's kind of moderate density gas, as is observed in CO. What about much higher density gas? You might imagine that there's a much stronger correlation between star formation and gas at much higher densities, because gas is, after all, forming out of the densest gas concentrations. So stars are forming out of the densest gas concentrations. So you might expect a stronger correlation. And indeed, there is a stronger correlation between star formation and gas, which is traced by higher density transitions. So this is showing the relationship between HCN luminosity and IR luminosity. So the HCN is a tracer of the dense gas. The IR is a tracer of stars. And this is this is a range of different, so this is both starburst galaxies, individual regions within the Milky Way, individual regions within other external galaxies. So this is putting everything on the same plot. And you can see that there's a close to linear relationship between the star formation and dense gas over a wide range of systems, over a wide range of scales. However, just as is true for moderate density gas, that kind of breaks down if you look at it in more detail. So this shows now the star formation. They define it as a star formation efficiency, but this is really just the star formation rate divided by the mass in dense gas. So that would be an inverse of the depletion time. That means that, so this is not a constant now. So this is, you might put an average value around here, but this is not a single constant, and it's in fact decreasing when you go to higher molecular gas content. So the dense gas is actually less efficient at forming stars at higher surface densities. So both for higher surface densities of gas, which leads to a higher molecular content, and also, as is shown here, higher surface densities of stars. So the efficiency of gas is actually lower at making stars when the old stellar gas content is higher. So you can also describe this another way, which is you can look at what fraction of the gas is actually dense as a function of the local environmental parameters. And here, this is showing the dense gas fraction as a function of average pressure, where the pressure you can write in terms of the gas surface density and the stellar density, and I'll talk more about this on Thursday, but that's the expected equilibrium pressure in a disk that has certain gas content and a certain stellar content, and that stellar content is just contributing to the vertical gravitational force. So where the pressure is higher, there's more dense gas, so there's an increase in the dense gas content at higher pressure, but that dense gas is actually less efficient at forming stars. So when you're going to a region at high total pressure, gas at the same density is less efficient at forming stars. So this is saying that actually all gas is not equal at a given density, whether it's a moderate density or high density. There is an environmental dependence. So there had been some ideas that there is above a certain threshold, everything can form stars, and I'll come back to those kinds of ideas. But really, it has to be, what this is saying, what these observations are saying, which is kind of what you expect theoretically, is that it's not just some absolute density, but there must be a relative density. That is, if the average density in some region is whatever you need to form HCN, then you wouldn't expect all of that gas to collapse. Only the higher density gas would be able to collapse. So it's not an absolute, but a relative effect. Okay, so why is there a correlation between star formation and molecular gas? So this is an empirical relationship. What is behind it? And in fact, theoretically, there's no real, there's this question of, is it causality? Does gas have to become molecular in order to make stars? Or is it really more of a coincidence? And a number of people have looked at that. And the reason is that, in fact, there's dynamically, the things that affect dynamics are really the temperature, which affects the thermal pressure, and the density, which affects gravity. But the chemical content doesn't matter except indirectly in setting the temperature. And the temperature is, in fact, not all that sensitive to the chemical content. And what's shown here is simulations where, so these are kind of individual cloud simulations where they vary what the chemistry is. So red is no chemistry at all. Green is including chemistry to make molecular gas out of hydrogen, and blue is all chemistry. And you can see that so this is the mass in stars that have formed as a function of time, and you can see that it's pretty insensitive to what the chemistry that's included. So, which is not really that surprising because, so that's saying that there's, in fact, it's not a causality, but it's more of a coincidence. And indeed, you expect molecular gas to form where densities are higher, where there's more shielding, and those are exactly the same conditions as you need for gravitational collapse to happen. So there's no reason, and in fact, if you look at the primordial universe, the chemistry was completely different, and yet stars formed somehow. So the gravitational collapse can happen. What the details of the collapse are, what IMF that makes, or how population 3 star formation differs from star formation at zero redshift, those may depend more sensitively on the exact chemical conditions. But whether star formation happens at all or not really is not going to be too sensitive to the chemical state. So the association of star formation with molecular gas, we think, is really more of a coincidence than causality. And this is just, again, showing you another aspect of that, which is the temperature. So this is where there's CO, so there's CO within this region here, and the temperature of that actually depends on the cosmic ray heating rate rather than on whether it's molecular or not. And this is just a different metallicity. So these things can, so other things can be affecting the temperature more than what the exact chemical content. Okay, so let me turn now to the relationship between star formation and gas in individual clouds. Using my mic here. Okay, so now this is looking at individual clouds. These on the left here, this is galactic plane clouds. This is nearby clouds. So this is Gould belt and similar clouds. This is clouds more in the molecular ring within our own Milky Way. Over here, this shows a collection of, I don't know if you can read the key, but the dots there here in these panels are from basically the same data as here, and these are otherwise from the LMC. So these colored dots are all from the LMC. And here, they're looking at star formation based on, looking and actually counting individual massive stars in the top column here. And in the bottom, they're using more traditional kind of extragalactic star formation tracers, that is H alpha and 24 micron combined. So those are just two ways of measuring star formation rates. And what's shown here is 1 over the depletion time as a function of cloud mass. Typically, so the first thing to notice is that there's a lot of scatter here. So there's sort of at a given cloud mass, there can be 2 or more orders of magnitude scatter. So there's not a kind of one-to-one relationship between observed efficiency and cloud properties. There's a wide range. And that's not too surprising because you could be catching a cloud at very different stages of evolution. Not only may clouds have stochasticity in their final star formation, but it hasn't in general gotten to its final star formation efficiency at the time you happen to be looking at it. So just in terms of the typical numbers, this is the average for the inner galaxy clouds. That's a depletion time of about a gigayear, which is kind of comparable to the extragalactic timescales, whereas for the nearby clouds, it's shorter. It's about 10 to the 8th years. And here for similar results hold for the LMC clouds. So so just again a comment that there's a distinction between the efficiency that you can observe, which is the ratio of the stellar mass of the total gas, versus the lifetime star formation efficiency, which is how many stars are you going to make out of this cloud. And you could think of this as a progression. So initially, the numerator is small, and you haven't reached the final value of the numerator. And at late stages, you no longer see the gas, so you would tend to perhaps even overestimate the star formation efficiency if gas has started to disperse. In the case where the star formation rate is constant, and also if destruction is rapid, then that would actually say that the mean observed star formation efficiency would be about half of the lifetime star formation rate. But actually, more generally, if you want to kind of turn this distribution of observed efficiencies into what is the average star formation efficiency over a cloud lifetime, you need to model the population rather than just have a very direct relationship between these. Okay, so those are, we still adjust this more. I think we're okay. You can hear me. You can hear me just fine. Okay, so of course there's much more extreme star formation in some places than we have in our own galaxy or even in nearby galaxies. And this is just showing from a recent paper that actually resolves individual star-forming regions in NGC 253, which is one of the nearest starburst galaxies where ALMA now is able to resolve down to basically a few parsec scales. And these are the locations of individual star-forming clouds. This is in dust continuum. So what's being observed here is the dust that's associated with the gas in these individual cluster-forming clouds. The masses, so this is for each of these individual structures. This is the turning the dust emission into a gas content, assuming some ratio of dust to gas and emissivity. This is the stars turning the Bremsstrahlung emission into a total luminosity, and then assuming an IMF, a mass of stars. So you can see that these masses are on the order of 10 to the 5 or even up to 10 to the 6. So these are quite massive clouds, but they're also forming a lot of stars. So actually, in this case, the star formation efficiency seems to be much higher in this kind of environment than it is in the environment that we have in, kind of normal molecular clouds in our galaxy. So this is saying that these low star formation efficiencies are not universal. It's just those are the properties that we have under more normal conditions. But when you go to extreme conditions, the star formation efficiencies in individual clouds can be much higher, up to, so certainly at least 10%, which is more like a few tens of percent is more like the maximum observed efficiencies in Milky Way kind of clouds. That's sort of the minimum observed efficiency in these more extreme star-forming environments. So this is saying that, the star formation efficiency depends a lot on the properties of the cloud, and you can get much more extreme clouds at much higher surface densities here. So this is the surface density averaged over the whole cloud. Instead of about 100 solar masses per square parsec, is 100 or 1,000 times as big. So this is much higher surface density and much higher volume density as well. So these overall densities in the cloud is more like the density within an individual core in a GMC, like those in our solar neighborhood. So these are really extreme conditions. Yep.
All right. What's the difference between this result and, can you hear me? Yeah, okay. What's the difference between this result and what you showed a few slides ago, which is that the ratio of the star formation rate surface density to dense gas surface density seemed to decrease at higher surface density, I think, which isn't that the opposite trend here?
So that is averaging over all of the gas. So indeed, if you average over all of the gas, the star formation efficiency at a given density is decreasing. But here we're not looking at we're not necessarily looking at a given density, but we're looking for an individual cloud. So that's the distinction, is you're looking at efficiency over the lifetime of a cloud, or attempting to infer that, versus star formation rate per unit time. So there's a time scale involved. The time scales here are all much shorter. So these time scales are quite short. So in fact, one way to interpret the other result is just that the time scale is shorter. And that there's, it's a question of how much gas do you have at these densities. So, but I'll get to that later. But yeah, so that's a good point, is that high efficiencies or low efficiencies, it's a question of what you're comparing to. Okay, so this is kind of putting out what are these different definitions of efficiency. You'll see different definitions of efficiency, and I think it's useful to kind of lay all these out. So the star formation rate, you can write in terms of the efficiency over the lifetime of a cloud, whether it's like a GMC in our solar neighborhood or like one of these extreme star-forming clouds in NGC 253. So there's a lifetime efficiency and a cloud lifetime. But you could also equally well write that in terms of the freefall timescale for that gas and the efficiency per freefall time. So those are just completely equivalent ways of writing that. And you can do that also if you're averaging, over if you're not looking at an individual cloud or the total molecular mass, but if you're kind of averaging over everything that you see in a beam, if you're putting together many clouds per unit area and many stars per unit area, you can still write these same things. So a depletion time of about 2 gigayears, which is kind of typical for nearby galaxies, would correspond to a lifetime efficiency of about 1% if the cloud lifetime, which is about 20 million years. That's what from looking at the association of star clusters with clouds in the LMC and in the Milky Way, it looks like kind of typical cloud lifetimes are on the order of a few tens of million years. And this will be better characterized with some of the new surveys that are being done now in other galaxies. But that would say that the typical efficiency over the lifetime of a cloud would be about 1%. And if you use an average density of gas, which is about 100 in terms of setting the freefall time, that would mean an efficiency per freefall time of a fraction of a percent. So that's kind of normal gas in normal galaxies. If you go to the starburst regime, rather than clouds being isolated structures, all of the gas is molecular because the attenuation of UV is so strong that basically there's very little dissociating radiation is able to reach most of the gas. So then if you write the star formation rate per unit area, that will be written in terms of the gas per unit area divided by the freefall time. But if the potential is dominated by gas, then the freefall time you can just write in terms of the velocity dispersion and the gas surface density, and that I've done here, basically assuming hydrostatic or hydrodynamic equilibrium. And then the star formation rate would scale as the quadratically in the surface density if the velocity dispersion is constant. And you'll recall from this for these starburst galaxies, the relationship between molecular gas content and star formation rate is basically looks like it's quadratic at high surface densities. And so you can interpret that as this kind of relationship with a given velocity dispersion and a constant value of the efficiency per freefall time. So that would be one interpretation. And then so if you did that, then if you had a velocity dispersion of order 10 kilometers a second, that would mean an efficiency per freefall time of about 1%. So one thing that I wanted to mention here, though, is that often you'll hear people talk about, per freefall time, but that is not the only dynamical time that's actually relevant. So a number of other dynamical times are also relevant. So one that may be even more relevant is just the vertical oscillation time in the gravitational potential. So the freefall time is only considering the gas, but actually the stellar content may be higher, and so the gravity due to the stars may actually be stronger than the gravity due to the gas. And so if you incorporate, so basically this is, if you only included the gas, this would look like the freefall time here, but if you include the stars here in that density, that's what sets the vertical oscillation time. And the vertical oscillation time, or this is the vertical crossing time is also related to the vertical oscillation time. So that is just the vertical oscillation frequency. So these other timescales this other timescale, and also there's the orbital time. So these may be equally important as the freefall time if the stars dominate the potential. But just the obvious point that all of these efficiencies, however you're measuring them, are pretty low. So star formation is said to be inefficient. Okay, so let me move on now and discuss the properties of giant molecular clouds and their dynamics. So yesterday I showed some of these from individual clouds. So here you can see this map of some of the Gould Belt clouds, and Orion is over here. Here's a nice map of Orion. And you can see, of course, the first thing you can see is that there's a lot of structure. So this is not noise, this is actual structure. And so here, so this is the cloud over. This is part of the CFA if you haven't been there. So this is so that's Orion A. This is Orion B, and you can see that those are where the gas is densest here and here. Those are the same regions where there's very active star formation as seen in the infrared. And you can also see the nebulosity in the optical even. So not naked eye, but it's there. Okay, so this cloud is, as I discussed, this is kind of a prototype for star formation. If you count up all the stars in Orion, it's about 1% of the mass. So this whole cloud has about 100,000 solar masses worth of gas in it. Only about 1% of that seems to have turned into stars up to the present time. And here's a much higher resolution image of Orion. I showed this to you yesterday. Here's the resolution. So this resolution goes down to 0.01 parsec this is actually the 13CO. I can't move my head, this falls off. And the velocity resolution is 0.1 kilometers a second. So this is very high resolution, both spatial and spectral resolution. And one of the things that the spectral resolution tells you is the nature, what are the kinematics, and in particular, that scale is showing you the velocity, and what that's showing you is there's very large velocity differences over this cloud, but on smaller scales, there's actually, there's a trend, you can look at velocity difference as a function of scale, and that's telling you something about the properties of the turbulence. So, how do we characterize turbulence in molecular clouds? Well, so one of the early ways, I think this was from 1980 or 81, Richard Larson pointed out that the velocity dispersion, if you look at different structures in star-forming regions, clouds or individual structures within them, there's an increase of velocity dispersion with scale. So suppose you're looking at a whole cloud, then you can characterize the velocity dispersion as, so this is kinetic energy, that's potential energy per unit mass. So you can characterize their relationship in terms of the so-called virial parameter. So the virial parameter would be 1 if this were in virial equilibrium. Of course, in general, these are not virial, these are not stellar systems, so they're very dissipative, and you don't expect any kind of equilibrium. But it's just kind of a number that you can use to describe the relationship between velocity, between kinetic energy and potential energy. And you can also write this mass in terms of the surface density averaged over the cloud and its scale, or the size of the cloud. And so then another way of, this is easier to stand here, you can write the velocity dispersion in terms of the virial parameter, the cloud size, and the surface density, or in terms of the volume density and the size. So that's at scales of whole clouds. Within the cloud, the velocity dispersion depends on scale within the cloud. And so you can take this relationship, so that's V at the scale of the cloud, and then say, okay, if you go to a smaller scale, what's the velocity dispersion on smaller scales? And it turns out that it has, that the velocity dispersion increases as roughly the 1/2 power of size within a cloud. And that was one of Larson's relationships, one of the relationships that Larson originally pointed out. In his original study, he suggested the power was about 0.38. From more, it seems closer to about 1/2 in more recent observational studies. And another way you can write this is in terms of so-called sonic scale, which is just defined such that the velocity dispersion at the sonic scale is equal to the sound speed. So this is just a definition of the sonic scale. given this relationship, you can define the sonic scale in this way. So from this definition, you can solve for what the sonic scale is, and you can write that in terms of the surface density or in terms of the volume density and the cloud size. Notice that if you use the surface density, it just depends on the surface density of the cloud. Typically, it's about 1/10 of a parsec for clouds as observed in the Milky Way, but you can see that this would, in general, depend on the surface density of the cloud. Clouds in the Milky Way actually tend to have relatively, the surface densities don't vary too much. In part, that may be a selection effect because you're looking at CO, and so you have you're only tracing a given range of density. So the sonic scale is typically about 1/10 of a parsec in nearby clouds. And you can also write the sonic scale using these relationships in terms of the Jeans length. Remember, the Jeans length varies as the proportional to the sound speed, inversely proportional to the density. So you can write that sonic scale in terms of the Jeans length, the velocity, and the varial parameter. So this shows from observations what the ratio of this velocity dispersion to square root of the size scale as a function of surface density. So this was that relationship here. So the velocity dispersion at cloud scales, you expect to vary as the linearly in the surface density and linearly in the radius. So if you take the square root of this, then the velocity dispersion should vary as the square root of the surface density and the square root of the size of the cloud. And that's what's shown in these solid lines here for different values of the that coefficient, which is related to the varial parameter. And you can see that there's a pretty, reasonably close to linear relationship. So that says that clouds are very roughly marginally gravitationally bound. So looking now at both whole clouds, so at this end is whole clouds, and then each of these whole clouds is connected by dots to substructure within the clouds. So this is using PCA to look at substructure within clouds. And you can see that the substructure within clouds follows that same, follows that 1/2 power relationship. So these relationships are for kind of two different reasons, in a sense. So this relationship has to do with being gravitationally bound. This relationship has to do with the character of the turbulence. So this is Berger's turbulence has this power spectrum as opposed to subsonic turbulence where this would be a 1/3 power. And what's shown here is the sonic scale where the velocity dispersion is equal to the sound speed, which is so this is 2/10 of a kilometer a second. So that's, as I mentioned, at a scale of about 1/10 of a parsec. If you just follow that relationship down to where the turbulence would become subsonic. Okay, so and I'll just say that simulations of turbulent magnetized clouds do very well in terms of reproducing the observed relationships between line width and size, and also the anisotropy, which arises as a result of magnetic fields. So on the left here are shown, the scale isn't very good, but the velocity dispersion as a function of size. So this is looking as a function of direction parallel and perpendicular to the mean magnetic field in simulations. These are more strongly magnetized simulations. These are more weakly magnetized. And this is for the torus cloud. You can see that there's a similar relationship, which is due to the anisotropy of turbulence in magnetized systems. And this is just each of these individual patches looking at that relationship. Okay, so I just mentioned magnetic fields. What do we know about magnetic fields? As I mentioned yesterday, typical magnetic field strengths in molecular clouds are, they start at about 10 microgauss, and then they can extend on up from that in very dense gas. So these are all from Zeeman observations from Chandrasekhar Fermi estimates. They're kind of similar. The magnetic field is increasing towards in high density gas. I'll talk about what this subcritical, supercritical is in a few minutes, or maybe more than a few minutes. So what's how are magnetic fields interacting with the gas? So this coupling, so the magnetic fields are well coupled, even though the clouds are kind of weakly ionized, provided that the collision time for neutrals and ions is high enough. And you can define a so-called ambipolar diffusion time, or ambipolar diffusion scale, which you can write down in terms of the alphane speed, which is b over square root of 4 pi rho, the neutral and ion densities, and the collision coefficient for ions with neutrals. And that will show you that the scale you expect to decouple is less than about 1/10 of a parsec. So that means that most scales within GMCs, but perhaps not within individual cores that are going to form stars, the magnetic fields are well coupled to the gas. So that means that even though it's not fully ionized, you can treat it as if it's ionized from the point of view of magnetic stresses on the gas. And I'll come back to that later on. Okay, so let's put some numbers on these timescales. So the gravitational freefall time is just a function of density. And this is written here in terms of the kind of typical average density in a cloud. So that's, several million years. The crossing time over, given that it's turbulent, you can define a crossing time. How long does it take the flow to cross over a given scale? And you could write that down in terms of the, if you set L is equal to the cloud scale, that would, and then this is scaling relative to a cloud of 10 parsecs. Typical clouds might be a few tens of parsecs. Typical velocities are a few kilometers a second. So the freefall time and the crossing time are kind of similar. That's another way of saying that turbulence is roughly, turbulent energy and gravitational energy are generally comparable. So at the cloud scale, you can take the ratio of these, and that you can write down in terms of this virial parameter, where this is saying that when the freefall time is equal to the dynamical time, clouds are essentially at virial parameter of 1. And if the virial parameter is larger than 1, then the freefall time exceeds the dynamical time. That is, gravity is less important than turbulence, or the gravity of that particular gas is less important than turbulence, which could be the case if the gas is confined in an external potential rather than the potential of that gas itself. Okay, so one thing to kind of immediately realize about the nature of turbulence, since it's so supersonic, that creates structure, and since the turbulent velocities increase with scale, that means that the structure also is dominated by the largest scales. And you can see that in observed clouds, and you could see that in the first simulations that were done of turbulent clouds with realistic kind of Mach numbers. And this is just from one of those early simulations that we could see at the time already, the structure that arises from the multi-scale turbulence. So one of the consequences of this is that star formation is not uniform through a cloud, but it tends to be in these filamentary regions, which is where the gas is densest. So that's not surprising. This turbulence tends to produce a distribution of either density or column density that actually obeys a log normal. And the basic reason for that is if you write down the continuity equation, you can write that down as in terms of the log of the density. And if you just say, okay, if I take the log of the density and I apply a compression and a shock, that will just either increase the log of the density by some increment or decrease it by some increment. And if you have a sum of random variables of either compressions or rarefactions, you would expect from the central limit theorem a Gaussian. So that's kind of the interpretation of why PDFs of density are log normal. So this is just showing what the relationship between in a simulation between the density and also that's on the left and the column density PDFs in comparison to Gaussians or log normal. And you can write what the mean of that Gaussian is in terms of the relationship between the mean and the variance. So a wider distribution also is more offset from 0 in terms of the mean, the median density or the mean density. And both of those are from simulations. The variance increases with the Mach number. So this is, you'll see people write down relationships like this. Sometimes they actually put an equality in. There's no real mathematical proof that this is the case. So this comes from numerical simulations. And the general relationship is this increase with some number here, which is maybe between about a third and a half. And there have been many simulations that have measured, this is just a few of those that have measured this relationship. So one of the things that you can try to do in observations is to connect the observed PDF, which is actually a PDF of column density, to the inherent PDF, which is a PDF of density. And you can try to do that based on also the spatial power spectrum of fluctuations that you can see, which is then telling you something about the line of sight averaging that goes from transforming this into this. And this is discussed in Brunt et al. So there are some assumptions that you have to make in this about the turbulence being kind of isotropic, which isn't necessarily true. But it's a way to, at least on average, if you're averaging over many clouds, to relate the density to the column density. Okay, so what's the consequence of this log normal distribution of densities? Well, there's a lot of volume at low density. But most of the gas is shifted to densities above the average value. And there's not just so here's the log normal, but in a self-gravitating simulation, the distribution will start out as log normal like this, but over time, a tail will develop. So there's a power law tail that develops, and that power law tail is, in fact, just the material that's gravitationally collapsing. So if you actually take, I'll talk about this in a little while, if you look at structures that are collapsing, they have a power law relationship between density and size scale, and you can actually turn that into what the PDF would be of mass as a function of size, and you get this. That explains the slope of that power law. But you can also see this distinction in observed clouds. So this is for quiescent clouds, Coalsack and Lupus, where you see pretty good log normals, whereas for star-forming clouds like Taurus, this is actually a more star-forming part of the same cloud, you can see this power law tail. And but also notice in the simulations that this part, the log normal part, stays the same at the same time as this log normal develops, as the power law develops at high density. Okay, so you might want to try to theoretically explain where these low star formation efficiencies come from, and there's a whole class of theories that tries to use this log normal PDF and then use that log normal PDF to try to make an estimate of what the expected efficiency per freefall time would be. So this is the freefall time I wrote down before, and you can write down what the star formation rate is in terms of that some efficiency per freefall time. And this is the thing that you want to be able to predict. And so if you have the simplest situation of a cloud with a given Mach number, virial parameter, and plasma beta, which is characterizing the energy density of thermal pressure relative to magnetic pressure or energy densities. Then those are the basic parameters that would describe a region in a cloud or a turbulent box in a simulation. These could also describe a cloud, although there are certain caveats in it, a real cloud. But so for these for these parameters that can describe the turbulence, you can ask, what should the free fall efficiency per free fall time be as a function of these parameters? And I've just listed here a number of people who have kind of developed theories of this. This is from one of the recent versions of this. And so what goes into this? So the basic idea here is to say something like the following. So turbulent can create structure, but turbulence can also destroy structure. So let's ask, what might we expect the requirements to be in order to have gravitational collapse? So you all know about the Jeans length, and the time scale for collapse is just the Jeans. If you have something that's just supported by thermal pressure and the size is greater than the Jeans length, then the collapse time is just set by the density. And that's just the Jeans length divided by, or proportional to the Jeans length divided by the sound speed. So the size scale associated with that is just comparable to the Jeans length. So, if you're thinking about a turbulent system, there will be some structures that are density high enough and have a high enough mass in a given region that they would satisfy that Jeans criterion. But there's also turbulence happening. So what is the turbulence doing? Given this relationship between line with size, you'd expect that that the velocity dispersion can, on average, tear things apart in a crossing time over so if you take the turbulent velocity dispersion at the scale and you take r at that scale divided by the velocity dispersion, that's kind of the time scale you'd expect turbulence to shred some structure. So that's what's given here. And you can write that in terms of the sonic scale and the sound speed. And then you can rewrite that in terms of the Jeans length because this r here is related to the Jeans length. So then the criterion for the collapse time to be actually shorter than the dynamical time with this dynamical crossing time or the shredding time corresponds to the Jeans length being smaller than the sonic scale in the cloud. And I wrote that down a few slides ago like this. So that would suggest that there's a critical density which increases as the square of the virial parameter and as the square of the cloud surface density, or you can also write that down in terms of the mean density in the cloud and the square of the Mach number. So there are a number of different ways of looking at this. Another way of looking at that is saying, okay, if you want something to collapse, it can, instead of saying, well, it's not shredded, you could say, well, I want turbulence not to support it. That actually leads to the same critical density. So some things, though, to keep in mind, you can say, gee, this looks great. But there's a number of assumptions that went into this. So one of the assumptions is that there's no correlation between density and velocity, saying we're going to sample from this turbulent velocity dispersion totally independently of what the density is. And that should, raise questions because, after all, the overdensities were created by the same turbulence that you're trying to use to either shred or support a cloud. So, that is, I think that's something that, is a caveat, which is an assumption that goes into these kind of classes of models, which is that density and velocity perturbations are totally independent of each other. So, these things, this can apply in some average sense, but in any individual cloud, it is not necessarily, you wouldn't necessarily expect these relationships to hold. So so what do you do next? So once you've identified a critical density, you can say, okay, so for everything above that critical density, I'm going to integrate under the log normal distribution, everything that's above that critical density, I'm going to say that can collapse. That gives you this error function. And then there's a time scale. In the original version of this from Krumholtz and McKee, they use the free fall time of the cloud as a whole. So their concept was you make structures over that crossing time or over the, which is proportional to the free fall time. And then you're only using the part of that, you're sort of refilling the PDF over that time scale, and then you're just taking the part that is available for collapse because it's not shredded and it's not supported by turbulence. And that gives a prediction for the star formation rate per free fall time with the virial parameter and the Mach number that looks like this. This has a kind of weak dependence on the Mach number, and the star formation rate per free fall time decreases at increasing virial parameter in this version of the theory. So there are different versions of this. Another version is from Padoan and Nordland that basically it's quite similar, but they argued that instead of using the timescale for the cloud as a whole, you should actually take the timescale at that critical density as the timescale for collapse. And you can work through, and that then changes the predicted star formation efficiency per free fall time by this factor. And then the efficiency per free fall time would still decrease with the virial parameter, but would increase with the Mach number. And as a few slides ago, here is a number of different versions of this theory. They each have their own version of the critical parameter and other kind of mechanics of how this works. Okay, so what do simulations show? Well, simulations do share some characteristics with these predictions, not necessarily the full dependence. But one thing that is quite clear is that the efficiency per free fall time from simulations, and these are simulations in which you just have a turbulent box, you drive turbulence to maintain a given Mach number, but you can turn up or down by changing the box size relative to the gene's length. You can turn up or down the ratio of the free fall time to the crossing time or the virial parameter. So doing that, and this is doing that so each of these points corresponds to a given Mach number for driven turbulence and to a given alphane Mach number, so that's relative to the alphane speed. But for different virial parameters with this relationship between, actually you can see it here as well, the virial parameter or the ratio of the free fall time to the crossing time. And what's very clear here is the strong trend towards decreasing efficiency per free fall time at high virial parameter or where the free fall time is large compared to the turbulent crossing time. So coming back to the observations, the efficiencies can be up to about 10% for the low mass clouds, but in the high mass clouds, the efficiency per free fall time seems to be pretty low. And for that to be consistent with for that to be consistent, these clouds would actually have to be quite unbound. So if the virial parameter were down here, the efficiency per free fall time would be, based on these simulations, several tens of percent. So most of the molecular material here, so this is not for individual clouds, but this is for averaging at a range of scales in a sample of so this is Feng's has now resolved a number of clouds down to, this is blue is 60 parsec scale. And this shows the efficiency, the histogram of the efficiency per free fall time. So the average value at these different scales is a bit less than 1%. So this is, you can look at individual clouds in the Milky Way and the LMC. You can look at whole galaxies at a range of spatial scales. The efficiency per free fall time is of order 1%. So that's saying that, we'd have to be around here in terms of the virial parameter. These clouds cannot be strongly bound. So if they're not strongly bound, what are they? They are kind of temporary concentrations, and I'll talk more about this, and Chenggu Kim will talk more about these simulations, I think tomorrow in his short talk. But really, we have to think about these molecular clouds. So if you think of these dark regions as star-forming molecular clouds, they have to be transient structures. So they can be temporarily self-gravitating, but they're dispersed by star formation, and they may be, not strongly self-gravitating to begin with. They may be really more, the concentrations may initially develop from the gravitational potential of the stars as much as from self-gravity. So the depletion time really must reflect global processes in the ISM, not just the individual properties of clouds. And I'll talk more about this feedback regulation on Friday. Okay. Thursday. I don't know. What's happening Friday? Something else. Okay. So let me go on now and talk about formation of individual stars. So that was kind of the properties on scales of clouds. Now let's kind of move inward to the scales of individual stars. So you may think, what does this have to do with galaxy formation? But all of those stars and galaxies are actually individual stars. So you want to at least have some understanding of individual stars. And I'll tell you that actually, I think, where'd Priya go? Anyway, so Priya said, we understand the IMF. We do not understand the IMF. So thank you for that confidence, but we don't understand the IMF. Okay, so what are the timescales involved? So I mentioned these before. The key point here is that going to smaller scales, so if you make L smaller or you make the density higher, you can get to a timescale that is shorter than the timescale for the cloud as a whole. So that means that you have a chance of forming stars in less than the time that this cloud will disperse. So that's good. If it weren't that way, then there would be no star formation. So let's focus in then on these regions of high density where star formation actually happens. And this shows, so this is from combined Herschel and Planck dust map, and then the locations of individual protostars and class 1 prestellar objects. So the class of a prestellar object is based on its spectral energy distribution and reflects essentially what the radiation field from the disk looks like. So this is for Taurus. Again, it's a dust map from Planck. And then here are the locations from individual protostars. So the protostars, I think you probably can't see these anyway, but the squares are class 1 stars or younger. So there's only 18 squares in this map. So those are the youngest protostars. And the asterisks are, each of these is a T Tauri star. So the T Tauri stars are not necessarily in the densest gas, but all of the protostars are in dense regions. And so I just brought this back to show you the polarization. The magnetic field is definitely playing some role in this of formation of individual stars. So this is just bringing back that as a reminder. And here is for some other clouds. The texture here, the drapery texture is showing the Planck polarization, and these are, I think those are infrared polarization from, let's see, I think those are near infrared polarization. Okay. So this is something that, so you can look at the individual molecular cores, which are the regions that may end up forming, although they don't all form individual stars, some of them may form individual stars. And this shows from Herschel, the locations of each of these blue symbols, I think those are triangles, is a location of a prestellar core that is an identified dense region in the dust map. the green is actual protostars. So those are, these are, the blue are things that may become protostars. The green are actual protostars. Here are some locations for molecular cores. This is also from a dust map in the Pipe Nebula. And so you can, with this many cores, you can actually start to do statistics. And this is the distribution of the prestellar core mass function from the Aquila cloud. So that's this from Herschel. So that's the core mass function. And this, as well as previous work in other clouds and other work, show fairly similar core mass distributions. So here's the core mass distribution. And then you can compare to the IMF. So that's, this is kind of what we're after. So we'd like to understand where the IMF comes from. And, what was pointed out starting out in the late 90s is that the core mass seems to be a shifted version of the IMF, shifted to slightly higher mass. So one initial interpretation of this is you form cores, and then a fraction of this mass makes it into the star, about a third of it being lost by in molecular outflows, which are seen to carry off mass from a significant amount of mass from protostars due to the disk winds, which the magnetocentrifugal disk winds, which are thought to drive those molecular outflows. So that's a kind of obvious, but not necessarily, that would be great if it were true, kind of thing. It might be true, at least in part, but there are issues there. But regardless of whether this relationship is everything, we'd like to understand where this core mass distribution, what the origin of that distribution is. And I should say that this is true not just in low mass clouds where it was originally studied, but also even in massive star-forming regions. So this is from an infrared dark cloud, and all of the structures that, so one thing that's important to keep in mind is that all of the structures where there is turbulence actually are seen to break up into substructures at high resolution. So these are structures that, when observed in higher resolution with the SMA, break up into substructures, where these substructure cores have masses comparable to the gene's mass. So it does seem like the gene's mass is relevant, but of course there's not just one gene's mass, because the gene's mass depends on density. Okay, so looking at individual prestellar cores, what are their properties? So how are we doing on time? Okay. See what I get through. So this is profiles of prestellar cores, and so they're actually quite similar to the what you expect for an equilibrium which is supported by thermal pressure. And based on the relative, so the turbulence does not seem to be very strong in these cores, and based on the relative numbers of these starless cores and stars of different ages, the lifetime of that stage seems to be typically a few freefall times. So for the this is right, okay. So the classical theory of these objects is that so if you just think about an isothermal sphere, something that's supported by thermal pressure, here's a sequence of these for a different ratio of central densities to edge densities. The Bonner-Ebert mass is the critical value, and above that, these structures would be unstable. Below that, they are stable. And so the Bonner-Ebert mass at the kind of typical density of a prestellar core is about a solar mass. So that's kind of interesting. Oh, I wrote an exercise for you. You can do that during lunch. So how do these unstable structures collapse? So this was first studied by Richard Larson and separately by Penston in the late 60s. So this is what Larson and also Penston found, that if you start with a uniform sphere, which is higher mass than this critical mass, it will collapse, and it will lead to this profile, which varies as the r to the minus 2, and the normalization is just proportional to the sound speed. So first you have this kind of outside-in collapse. So the collapse starts in the outside, works its way to the inside. And then after you've achieved this asymptotic profile, then there's a wave of rarefaction that propagates. So first there's this collapse, and then you can think of it as infall of material. This rarefaction as material actually falls into the star, or to this forming star. So, and the basic reason for this is first you have to achieve, everywhere has to first become equally genes unstable, and then you go to the region that has the shortest timescale, which is at the highest density in the inner part, and that collapses first. And so you don't have to have an idealized spherical structure in order for this, to actually get this Larson-Penston solution. Just about anything. So if you have a turbulent cloud and it makes a core within it, you will get this Larson-Penston profile, and then the rarefaction that material then propagate, the collapse then, so it's sort of outside in and then inside out. It's a very general solution. I guess I don't have time to talk about important numerics, but in simulations we always have to replace collapsed regions with sink particles, because otherwise the simulation grinds to a halt and you're done. So if you want to actually follow star formation, you need to introduce sink particles. So how do we, there are a lot of important questions related to the CMF and the IMF. I don't think I have time to discuss all of these. I wasn't even planning to discuss all of these, fortunately. So I won't try to, so there's both kind of theoretical ideas for what sets the peak of the CMF and what sets the high mass slope of either the CMF or the IMF. There are kind of different theories that relate to different of these. I will highly recommend a review in Protostars in Planet 6 by Offner et al., which discusses these both the theories and simulations of the CMF and the IMF. So please read this for to learn about it. I have a little time, so I'll say a little bit about the peak of the CMF, which is related. I think that there's a little bit. It's a little bit simpler. So I'll just say a little bit about this. Okay, so the gene's length you can write in terms of the density and the temperature, and we don't think the temperature varies very much within clouds. But what density should we choose here? Well, you wouldn't want to choose the average density in the cloud, because that average density is not really representative of the material that's collapsing. Perhaps a better density to choose would be the characteristic post-shock density, at the, using the Mach number. So if you use that post-shock density, you've increased the density here by a factor of the square of the Mach number, and you can write that down in terms of the virial parameter and the cloud surface density, and put that into the gene's mass here. And that says that the gene's mass, if you use the post-shock Mach number, just varies inversely with the cloud surface density. So putting in kind of typical numbers, that does give you a scale that's comparable to a stellar mass. And the Bonner-Ebert mass is actually, critical Bonner-Ebert mass is actually about a fifth of the gene's mass, so that really brings you kind of close to a solar mass. If you, do what outflows do, you'd expect to reduce that by about a factor of 3. So that gets you down to a kind of interesting mass in terms of the relationship to the IMF. So you can, I won't go through how this is set up, but you can look at this with simulations and ask, is there in fact this expected relationship between Mach number and the peak of the core mass? And indeed, this does hold in simulations. Both the peak of the core mass and not all of those cores are self-gravitating. So what's shown here is the self-gravitating and the non-self-gravitating. But the tail doesn't seem to, if you just look at these cores, the tail does not seem to be consistent with that power law slope. So one suggestion for how you get how you get stars up to very high masses, considering that there's tends to be fragmentation that brings the core scale to lower mass, is this idea that actually you can have initial cores that form by fragmentation at close to the gene's mass, but then they can continue accreting from the ambient environment. So this was originally, there was actually earlier work even before this, but the idea is sort of competitive accretion, where there's Bondi-Hoyle accretion, which depends on the rate depends on the initial core mass, or it's a subsequent mass. As this grows in mass, then it's more competitive. Of course, this is a turbulent medium, and so then you need to replace the Mach number by something that depends on the turbulence. So this was originally posed, but a critique of this is that if you think about this and you use the Bonner-Ebert mass as this original mass, then you can kind of put in the numbers, and this is the original accretion rate. So the accretion rate from Bondi-Hoyle accretion, if you're starting with that core mass, would actually scale as the inverse fifth power of the Mach number. So that seems bad, because clouds are, turbulence is hypersonic, so that if that Mach number is 10 or more, that's pretty bad in terms of, really suppressing accretion. But in practice, these cores are not accreting from ambient conditions. They would be accreting from the filament in which they were born, which would have lower Mach number because it's a post-shock region, and higher density. So I would say that it's not unreasonable for, and certainly we see in simulations that cores do continue to accrete even after their initial formation. So what about magnetic fields? I can still sneak in a little bit about magnetic fields. This is important, so I'll do that. So going back to the early work on, kind of general theory of star formation, Mestel and Spitzer pointed out that if you want an object to be able to contract gravitationally, it has to have gravitational energy that exceeds the magnetic energy. So the reason this is important is if you take the ratio between these, it's actually a conserved quantity. So if the gravitational energy, it's not like the gravitational energy could get ahead later. The ratio is always conserved. So you'd always have to, you not only have to start with, but you would always have the gravitational energy larger than the magnetic energy. And you can see that the ratio of these is just depends on the mass to flux ratio, where the flux is just should have been a B here. Flux is the area times the magnetic field. So if you do the more exact solution, there's a mass to flux, a critical mass to flux that looks like this. So just the value just depends on Newton's constant. You can do the same thing for magnetized sheet. That's what's shown schematically here. And that leads to a critical length along the field. So that's critical length along the field, which depends on the magnetic field strength and the density. So if you take that critical length and you carve out of your cloud a sphere of that diameter at a typical density and magnetic field strength, that's an incredibly large mass. Okay, so that seems really bad. So magnetic fields seem to be able to, would seem to be able to very much suppress star formation, because all stars are not above 40 solar masses. So, this seems bad. But in fact, observed cores are actually, they are actually supercritical. So how did they get that way? The early theory was that they got that way by ambipolar diffusion. Basically, the neutrals would cross magnetic field lines, but the timescale of that seems to be typically about 10 times the dynamical time, whereas cores don't really seem to be able to live that long. So one of the ways around that is to, not do this by taking that whole diameter, but actually do this anisotropically. And I won't go through the details here, but you can show that if you basically accrete along the field lines, then you only need to have the critical length along the field line, and you can use something much more like the gene's length in the perpendicular direction. And you end up with a mass scale which is set by the post-shock magnetic field strength, But that post-shock magnetic field strength just depended on the large-scale pressure in the cloud to begin with. So you're kind of just back to the initial result, which is the mass just depends on the mean density in the cloud and the Mach number. And so it's essentially the critical Bonner-Ebert mass, but using the turbulent pressure in the cloud, which then sets the post-shock magnetic field strength that then controls the evolution until you get a supercritical region. And this just shows that based on, both the simulations are consistent with the theory and also agree with the masses of observed cores. So that's the magnetic field looks like it will totally suppress star formation, but actually you can get to quite reasonable supercritical core masses just by accreting anisotropically, which is reasonable in a dynamical cloud. Okay, so do go read the review. This is quite interesting to tell you about the state of things. I think that we're a little bit further with understanding the CMF than we are with other aspects of the IMF. One of the things that might suggest is that, at higher pressure, the CMF certainly would, at higher pressure, the CMF would suggest a CMF that would have a characteristically lower mass. There's been some suggestion that might be the reason behind the bottom-heavy IMF in massive ellipticals. Whether that's true, it's hard to say because, after all, that's only the CMF. There's a lot of other things that that need to happen before you get the IMF out of that. And so I think I'm done here. I'll just say that there are simulations of this, but these generally start with conditions that are already a star cluster. So you'd have to worry about how did the material already collect to a very high density, without fragmenting. That's still not well understood. So I think there's still a lot to be done on understanding the IMF and the fragmentation to reach individual stars in molecular clouds. Okay, so done here. And next time I'll move on to how feedback actually self-regulates star formation. Okay.
Thank you for being perfectly on time. So, questions? Yes, please.
Okay, so you were talking about the mass to flux ratio.
Yes.
So with the flux, the area there, is that just the plane of sky area? Because
so the area is the area perpendicular to the magnetic field.
Okay.
So if you have magnetic field going through like this, you're always measuring. I mean, it's really only well defined for a given magnetic flux tube, but
okay. Yeah, because I was thinking, if div b is 0, then if you consider the surface of an entire cloud, then
yeah.
there should be no flux.
It's actually going. It's some area. So you're looking. So you're kind of thinking, in what orientation do I have the largest magnetic flux? And that's the way you can kind of measure it in simulations, at least, where you have the freedom to adjust, what your area is. So if you put it sideways, then you'd have 0 flux through it. So yeah.
Okay. I have one more question too. Also, so for a lot of these models, you were talking about the gene's length, and that was an important parameter here. So doesn't that mean you're assuming that all these clouds are spherically symmetric and uniform density?
No, not at all.
No?
So I mean, there's still so the Bonner-Ebert mass is just about 1/5 of the gene's mass. So the gene's mass is really just saying it's a characteristic scale that's related to density, and so it's not that we really think that you have some uniform medium with perturbations that's fragmenting. It's really better to think of it as it gives you a characteristic mass scale at a given density. Okay. So something has to be larger than that mass scale in order to collapse, if that's its average density. So it's a better way to think about it than as an instability. It's really more a measure of the ratio of gravitational energy to thermal energy.
Okay, you have a question there?
So quite some time ago, you showed the data from Big Eel 2008,
yeah.
And you had like their plot on the left. I think this was about like 70 slides ago, so it might take a while to go back. But
no, that's the magic of sliding.
the magic of slides. Okay, so what my question is, on the right you showed I think some LMC data, and that follows like a much tighter relation. So could you explain the scatter in this Kennecook-Schmidt type thing with different gas properties, or is the scatter
or different
just,
XCO?
Yeah.
I mean, I think
I guess my question is this scatter inherent, or do we think that this comes from some particular?
So I think one thing is that the scatter is scale dependent. So the more you're averaging over, the more you can reduce the scatter. There's also certainly in the molecular content, there's definitely variations with XCO. These are all assuming the same XCO. So yeah, I think so certainly you do expect somewhat different properties, but there's also observational calibrations that go into this, and on this, in the star formation tracers as well, there are observational calibrations as well.
Yes, another question.
Is there anything known observationally about the star formation rate dependence and the IMF shape dependence on the magnetic field?
Oh, no, because the magnetic field is not. The magnetic field is so you don't know it. There are not very accurate tracers of the magnetic field to begin with. So that is definitely not something that there's any there's no really measured correlations between those.
Question from a student down there.
Why? It's funny. My question is, how robust is the determination of the peak of the CMF, given that, as you showed, when you increase the resolution of your telescope, you tend to fragment things in smaller thing. And since we are not all the way down to the turbulent cascade, I'm wondering if
I agree that's an issue. I mean, they say that it's, you're pretty close to France. You can go over there and ask them.
That's a good answer.
So there are some issues about how well resolved it really is.
Final question before we break for lunch.
From a student?
Oh, from another student.
Distribution could be the sources, the radiation from nearby sources. Are we closer observationally to study that more than magnetic fields?
So changing the distribution, you mean based on?
Just the ionizing sources,
but
changing
these
the
are
fragmentation.
But this is not ionized. This is not ionized gas. So.
Sure, but as you start forming some of the stars, they will start impacting the media. So that might change how the rest of the fragmentation
In fact, it doesn't seem to be that different in Orion, say, from the lower mass clouds. But that's, the molecular gas is by definition protected. So, so once you're at a high AV, definitionally it's not seeing the ionizing radiation. So in fact, once you have, there is still the infrared, which can raise the temperature a little bit, and so that can affect, if you really believe that the mass scale is set by the Jeans mass, that goes as the square of the temperature. So if you increase the radiation field locally, even if you're not seeing ionizing radiation or even non-ionizing UV, it's still, higher. It still would, have a higher infrared field, which could, at least in high density regions, that can raise the temperature.
Okay, we should thank again Eve and Priya. So thank you very much again.